At SME Algeria, the MG-MH365 plate bending machine performs the core operation of curving thick steel plates with force and precision. This powerful, four-roll hydraulic machine is designed to handle large-scale industrial bending with high repeatability and reduced manual intervention. The process begins with the operator positioning the flat steel plate onto the feeding rollers. Once aligned, the side rolls automatically rise to begin the pre-bending phase. This ensures minimal flat ends at both edges. The top roll applies downward pressure while the lower rolls move in sync, guiding the material through a controlled arc. Before full bending begins, the system runs a brief calibration cycle to verify plate alignment and pressure distribution. Throughout the operation, hydraulic pistons regulate the movement of the rolls with real-time feedback, allowing precise adjustment based on the material's thickness and desired curvature. This machine can bend plates up to several meters in width and is capable of producing cylindrical or conical shapes, depending on the roll positioning. The integrated control panel gives the operator full command over bending parameters, including pressure, rotation, and positioning. This helps maintain consistent results across repeated cycles. After the initial pass, the plate may be rotated and fed again to complete the final shape. The MH365's robust frame reduces vibrations and ensures stability even under extreme loads. Its ability to form large components with minimal distortion makes it well suited for applications in shipbuilding, energy, and heavy industry. Through automated precision and hydraulic power, this bending process turns rigid steel sheets into accurately shaped structural components, ready for final welding, assembly, or deployment. To make auger flights in a garage setting, segments are first calculated and marked on blanks. Each sector is cut out and welded together. The spiral is then stretched to the required pitch. A flange is tack welded, followed by final welding to the central pipe for assembly. In this video, we take a detailed look at the rotor winding process for a 300 kilowatts Kato motor at Aflo Motors. The process begins with preparing the rotor core, cleaned and checked for dimensional accuracy before proceeding to the next phase. The first step in winding involves setting up the copper wire. Technicians measure and cut lengths with care, ensuring consistency across each winding. Insulation is then added manually to prevent short circuits during motor operation. Next, the winding begins. Each copper wire is methodically looped into the rotor slots. The placement must be precise to ensure balance and uniformity, both crucial for the motor's long-term efficiency and vibration control. To secure the coils temporarily, technicians use binding tape and insulating wedges before the resin process. The rotor is then inspected to confirm that all windings are seated properly and that slot fill is uniform. Electrical continuity is checked with specialized tools to detect any defects before curing. Once winding is complete, the rotor undergoes thermal insulation treatment. It is placed into a heated oven where resin cures the coils, locking them in place and enhancing durability. After curing, excess material is trimmed, and the rotor is cleaned again to remove any residue. The rotor is then sent for dynamic balancing. At high rotation speeds, even slight imbalances can lead to performance issues. This stage uses specialized balancing machines to ensure flawless rotation. In the final steps, technicians perform a high-voltage insulation test, checking for any potential breakdowns. If it passes, the rotor is ready for integration into the motor casing. This entire process combines skilled manual labor with technical precision, ensuring that each 300 kilowatts rotor can deliver reliable power in demanding applications. We explore how extruder feed screws are manufactured, rebuilt, and designed for use in plastic injection molding, extrusion, and blow molding processes. The journey begins with analyzing the application requirements. Factors like resin type, throughput, and temperature help determine the right screw profile. Engineers may also review historical wear data to further refine the design for improved longevity. Raw steel bars are selected and machined to form the screw core. CNC lathes shape the outer geometry, while precision milling is used to form the flight profile. These flights are then hardened through heat treatment for durability under high-pressure conditions. For rebuilding, worn screws are inspected and reconditioned. Damaged flights are repaired by welding, followed by remachining to restore original dimensions. In some cases, screws are renitrided or chrome-plated to extend service life. Custom screw designs are created using CAD modeling and performance simulations, optimizing for melt uniformity, shear rate, and energy efficiency. Technicians test each screw to ensure dimensional and performance standards before final delivery. This integrated process, combining design, machining, and repair, supports efficient, high-quality plastic processing across diverse manufacturing environments. Spiral drills are essential tools in modern machining, used across industries to bore precise holes into solid material. As CNC-controlled processes evolve, the demand for faster cycle times and tighter tolerances places high expectations on the tools themselves. This video takes you inside the production of Titex Plus spiral drills, where precision is engineered from the ground up. The process begins with CAD-based design. Engineers create technical drawings that double as production blueprints, defining all machine settings and parameters. These digital models allow for consistent replication and seamless integration with downstream machinery. For drills up to 12.7 millimeters in diameter, raw blanks are peeled from coils. Larger sizes are cut from solid bars. Some are machined directly on automatic lathes, while others are made by welding together segments of high-speed steel and tool steel. This flexibility in blank preparation accommodates various material grades and application demands. At this early stage, the soft blanks are prepped. Tips are chamfered for easier handling and orientation. Chamfering also improves centering during the initial grinding phase, reducing vibration and tool deflection. Then comes heat treatment. The blanks are heated to 1,200 degrees Celsius inside vacuum furnaces. The vacuum environment protects the steel from oxidation. As the cycle ends, nitrogen gas floods the chamber, quenching the steel. This is followed by several tempering stages at 550 degrees Celsius, reducing brittleness while increasing overall hardness. These heat cycles are tightly monitored to ensure uniform metallurgical properties across batches. Next, hardened blanks are ground to their final diameter using centerless grinding. The iconic spiral shape starts to take form as flutes are ground into the tool body. Secondary grinding processes follow to create the clearance behind the cutting edge and refine the overall geometry. Complex contours are achieved using CNC-controlled multi-axis grinders. Point grinding gives the tip its final form, preparing it for high-precision drilling applications. Some drills receive a black oxide surface through steam treatment. This involves exposing the drills to superheated steam in a tempering furnace for about an hour, enhancing wear resistance and corrosion protection. High-performance variants are coated with hard layers such as titanium nitride, tin, titanium aluminum nitride, TiLN, or titanium carbon nitride, titanium 1 cyanide. These coatings are applied via physical vapor deposition, PVD, in specialized chambers where the coating material is vaporized and deposited onto the tool surface. The process requires thoroughly clean drills and strict environmental controls to ensure layer adhesion and durability. Layer thickness, usually between 1 to 4 microns, is optimized for specific operating speeds and materials. To maintain consistent quality, statistical process control is applied throughout production. Samples are checked regularly to catch any dimensional or structural deviations early. This methodology is part of a broader ISO 9001 certified quality system implemented at the facility. Finally, each drill is marked by laser engraving or stamping indicating brand, material, and diameter. The finished tools are packed and stored in high bay warehouses, awaiting shipment. The Titex Plus line offers a wide range of drill geometries tailored to different applications. Among them, high-performance types like Alpha 2A4 and Megajet stand out for their cutting speed, hole quality, and extended tool life. These drills help manufacturers meet performance demands while optimizing cost efficiency, delivering reliable results even under challenging conditions. In this video, we delve into the intricate process of manufacturing power press machines, vital equipment in metal forming operations such as punching, stamping, and bending. The journey begins with the construction of the machine's frame, which serves as its backbone. High-quality steel plates are selected and precisely cut using advanced methods like laser or plasma cutting. These plates are then thoroughly welded together to form a robust and stable structure, ensuring the machine can withstand immense operational forces. Following the frame assembly, attention shifts to the machining of critical components. The ram, flywheel, clutch, and crankshaft are crafted with precision to ensure smooth and efficient motion transmission. These parts are typically produced using CNC machines, which offer high accuracy and repeatability. Once machined, components undergo heat treatment processes to enhance their strength and durability, preparing them for the rigors of continuous operation. The assembly phase integrates all these components into a cohesive unit. The ram is aligned within the frame, connected to the crankshaft and flywheel system, which is powered by an electric motor. This setup converts rotational motion into the linear motion required for pressing operations. Precision in alignment and assembly is crucial to ensure the machine operates efficiently and safely. After assembly, the power press undergoes rigorous testing to verify its performance. This includes running the machine through various cycles to ensure consistent operation and checking for any anomalies in motion or force application. Adjustments are made as necessary to fine-tune the machine's performance. The final steps involve surface finishing and painting to protect against corrosion and wear. Safety features, such as guards and emergency stop mechanisms, are installed to ensure operator safety. Once all checks are complete, the power press is prepared for delivery, ready to perform in demanding industrial environments. This comprehensive manufacturing process ensures that each power press machine delivers reliable performance, precision, and longevity, meeting the high standards required in metalworking industries.
10. Del Modello alla Fusion 537. https://www.youtube.com/watch?v equals Zybom 43I1Y. In the heart of a foundry, the transformation from model to cast iron product is a thorough process that combines traditional craftsmanship with modern technology. This video offers an in-depth look at each stage of this transformation. The day begins with the furnaces already operational, ensuring they reach the necessary temperatures for melting iron. These furnaces run continuously, monitored by skilled operators to maintain stability. In the molding department, a substantial base model, crafted in 2 parts, is prepared. Each half must align precisely, as even minor shifts can compromise the mold's integrity. After applying a release agent, the model is placed within a large steel flask. This flask is then filled with a special sand-resin mixture. The mixture must be tightly packed to eliminate air pockets that could distort the casting. As the sand hardens, it captures the exact shape of the model. To identify the mold, operators imprint the client's name onto the sand. Approximately 10 minutes are needed for the sand to solidify. Once hardened, the mold, now containing the model's imprint, is lifted. Certain parts of the model are manually removed to prevent damage to the mold. Careful extraction is essential, especially for internal cavities and detailed contours. The mold surface is then treated with an iron oxide coating, enhancing the quality of the cast iron surface. This coating forms a protective barrier that also improves thermal resistance. The coating is dried in a furnace. The 2 mold halves are positioned side by side, and the core is carefully placed within the lower half. Positioning the core is a delicate step. It must remain suspended without shifting during the pour. Metal spacers and pins are sometimes used to maintain exact spacing between mold sections. The mold is now ready for pouring. Each mold must also allow for proper venting, enabling gases to escape during pouring without compromising the final shape. Before the pour begins, all molds are double-checked to ensure no deformation or contamination has occurred. Even a minor misalignment at this stage could compromise the entire casting. The following day, a large mechanical arm dismantles the casting, freeing it from the sand. A probe measures the temperature of the molten iron, ensuring it has reached the required 1,500 degrees Celsius. Consistency at this stage determines the structural properties of the final product. Any slag remaining on the surface is removed. The iron is melted in an 18-ton oxy-combustion rotary furnace. This type of furnace allows for faster melting and better energy efficiency. The second half of the mold is rotated 180 degrees and placed atop the first, creating a cavity reduced by 1 centimeter to determine the final thickness of the cast iron. During pouring, operators carefully monitor the flow rate and filling time to avoid turbulence and trapped gas. Once the metal enters the mold, it begins to cool and solidify rapidly. The cast piece is left to cool naturally for several hours before further handling begins. After the casting process, small steel spheres are blasted onto the surface for several minutes, cleaning and smoothing it. This shot blasting process removes residual sand and oxides. All subsequent processing steps are carried out in the NIRI department. This comprehensive approach, from model creation to final casting, showcases the precision and care involved in producing high-quality cast iron components. Every stage is a testament to both engineering discipline and the hands-on skill of foundry workers.
In this behind-the-scenes footage from NASA's Kennedy Space Center, technicians inside the Vehicle Assembly Building carry out a critical inspection of the Space Shuttle Discovery's external fuel tank. Following a scrubbed launch attempt on November 5th, teams began a thorough process to investigate structural anomalies. The external tank, covered in foam insulation to regulate temperature, is first stripped of selected foam sections. Technicians use hand tools to gently remove insulation from specific regions, allowing direct access to structural components underneath. This work focuses on the intertank area, a zone housing structural supports and key instrumentation. Attention centers on two 21-foot-long U-shaped aluminum brackets that showed cracking. These brackets, vital in holding structural loads, underwent damage that halted the original launch schedule. With insulation cleared, technicians inspect the brackets visually and prepare them for advanced imaging. Next, X-ray-style non-destructive testing methods, similar to industrial radiography, are employed. This scanning allows teams to examine the internal structure without causing further damage. The goal is to verify the extent of cracking and determine whether repairs are sufficient for future flight. Sensors mounted near the affected brackets are also removed and tested. Engineers assess whether the instruments recorded relevant strain data during pre-launch events. This process is part of a broader safety review that ensures all components meet strict flight readiness criteria. It highlights the high-stakes precision required in human spaceflight, where even minor structural defects demand detailed analysis before a mission can move forward. Heat treatment plays a crucial role in shaping the strength and accuracy of gears. In this facility, robots control the process to minimize distortion, an essential step in producing high-precision gear components. The sequence begins with carburizing, a heat treatment method where carbon is diffused into the surface of the gear. Gears are placed into specialized furnaces, where they are exposed to carbon-rich gases at high temperatures. This step hardens the outer layer while keeping the core tough and ductile. To ensure uniformity and repeatability, robotic systems handle loading, unloading, and monitoring. Automation enables tight control over time, temperature, and atmosphere inside the furnace, helping reduce distortion caused by thermal stress. The 141.6-meter yacht Nord began her maiden voyage after completion. Each phase, from hull construction to final detailing, required expert coordination and craftsmanship.
At the heart of this facility, a massive washing drum measuring 4 meters in diameter and 10 meters in length comes to life. The process begins with assembling the drum shell from large steel segments, welded together with precision. Internal supports and baffles are then installed to control material movement during operation. Next, a ring gear and trunnion rollers are mounted to ensure smooth rotation. Workers install heavy-duty flanges at both ends, which will later connect to drive systems and material feed points. Lifting equipment maneuvers each section with millimeter accuracy. After assembly, technicians check concentricity and alignment to prevent imbalances during high-speed rotation. Final inspections verify weld integrity and structural stability. This drum, destined for a mining or aggregate facility, is built to endure years of continuous operation in extreme conditions. In modern littoral warfare, detecting and neutralizing submarines in shallow, cluttered waters demands both speed and precision. Saab's lightweight Torpedo, or SLWT, is engineered to meet that challenge. At just under 3 meters in length, the SLWT carries a powerful warhead and advanced homing capabilities within a compact design. The engagement begins with real-time sonar detection, either from a Visby-class corvette or an NH-90 helicopter equipped with dipping sonar. Once a probable submarine contact is identified, the SLWT is deployed. Launch methods include surface ship tubes or airborne deployment, offering flexibility across operational platforms. It can be launched autonomously or manually, depending on mission parameters and threat level. Operators can pre-program search patterns or let the torpedo make dynamic path corrections mid-mission. This flexibility increases effectiveness in both open sea and congested littoral zones. Once in the water, the torpedo achieves neutral buoyancy to avoid premature contact with the seabed. It then activates its homing system, scanning wide areas using both passive and active sonar. The onboard computer continuously adjusts its path to track and intercept the target, even in environments with multiple acoustic signatures. Its propulsion system allows for silent, sustained travel, while optional two-way communication enables mid-course updates or abort commands. The torpedo can adapt in real time, switching from broad search mode to precise terminal homing as it nears its target. Upon confirmation, the warhead is triggered, delivering a decisive blow. The SLWT's Integrated Control System, ITEC, ensures complete coordination between detection assets and weapon deployment. This unified approach allows for rapid, informed decision-making in high-stakes scenarios.